Hello everyone, I am Jimmy Hu. I'm here to present our paper called Pose2Gaze, eye body coordination during daily activities for gaze prediction from full body poses. The co-authors are Jiahui Xu, Xin Simit, and Aaron Budin, we're from University of Stuttgart, and Bionic Intelligence, Tübingen, Stuttgart. Here is the outline of my presentation. I'm going to introduce the research background, related work, analysis of eye-body coordination, method, results, discussion, and conclusion. Human eye gaze is important for many applications in VR, AR, and extended reality. For example, the gaze contingent rendering is an important application, and also gaze-based interaction, gaze-based visual element optimization, and also gaze-based activity recognition. Well, the motivation of our work is that we observe that the human eye and their full body movements are coordinated in daily activities. For example, in this figure, we can say that in daily pick and place activities, the human eye gaze and their body movements, they are coordinated with each other to finish the corresponding task. In this paper, we want to explore the coordination between eye and full body movements, and we try to predict eye gaze from full body poses. The main contributions of our work are listed as follows. First, we provide comprehensive analysis of eye-body coordination in diverse human object and human-human interactions. We propose a novel method that combines a convolutional neural network and a spatial-temporal graph convolutional neural network to predict eye gaze from full body poses. We conduct extensive experiments on 4 public data sets to demonstrate the effectiveness of our method, and we conduct experiments on the downstream task of gaze-based activity recognition to show the benefits of our method. Here we are going to introduce the related work. Well, previous have explored the eye-hand coordination between eye and hand movements, and also previous have explored the eye-gate coordination between eye and gate, and also the coordination between eye and head, eye, head, and torso. However, previous works they usually focus on correlations between eye gaze and specific body parts, for example, the hand, head, or torso. Well, our work simultaneously investigate the coordination between eye gaze and the full body movements. To do the analysis, we use 4 public data sets, namely the MoGaze, ADT, GIMO, and EagleBody datasets. Those datasets are collected in real-world VR and AR environments, and they cover the human-object interactions and also human-human interactions. We first analyze the correlations between eye gaze and body orientations. This table shows the correlation between eye gaze and different body drawings, and we can say that the gaze direction is strongly correlated with the body orientations. And also we find that with the head orientations, the eye gaze has a very strong correlation with head orientations. We first analyze the correlations between eye gaze and body motions. We find that in the human object interaction activities, the human eye gaze had strong correlations with body motions in such kind of activities. However, we observe that in the human-human interactions, the eye gaze direction has little correlation with the body motions. Well, to understand the human-human interactions, we further analyze the correlation between eye gaze and the directions pointing from a person's body to the body of the interaction partner. We try to analyze the correlation between the eye gaze direction and the directions between 2 bodies. Well, we find that in this situation, the eye gaze has a very strong correlations with the directions between 2 bodies, which means that in human-human interactions, the human eye gaze is strongly influenced by the body pose of the interaction partner. Well, based on our method, we propose a method called Pose2Gaze. The Pose2Gaze method contains three components, namely the body orientation feature extraction, the body motion feature extraction, and the eye gaze generation. Well, for the body orientation feature extraction, we use the head directions as input because head orientations have strong correlations with the eye gaze. We use a 1D convolutional neural network to extract the features. For body motion feature extraction, well, in human object interaction activities, we use the full body pose as input because the body pose are strongly correlated with eye gaze. And in human-human interactions, we add the body pose of the interaction partner as input because the body pose of the interaction partner has influence on the eye gaze. And we use a spatial temporal graph convolutional network, which consists of a temporal graph convolutional network and a spatial graph convolutional network to extract the features from body motions. Finally, we concatenate the features from the body orientation and the body motion, and then we use a 1D convolutional neural network to generate the eye gaze. Well, to evaluate our method, we use three different eye gaze generation settings. Namely, we generate eye gaze from body pose in the past. This corresponds to the setting of eye gaze forecasting, namely using body pose in the past to generate eye gaze at present. We also generate eye gaze at present from pose at present. This corresponds to the eye gaze real-time estimation, and we also generate eye gaze at present from the body pose in the future. This corresponds to the offline generation of eye gaze. This table shows the gaze generation performance at different data sets. Well, we can say that for the three different eye gaze generation tasks and for different data sets and for different activities, our method can achieve better performance than prior methods in terms of the mean angular errors. Well, this figure shows some of the visualization results. We can say our eye gaze predictions is more close to the ground truth eye gaze than other methods. Well, this video shows some of the visualization results. We can say that at different data sets, at different activities, our predictions is more close to the ground truth than other methods. We also performed an ablation study, namely we remove different components used in our method and test their effectiveness. We find that our method consistently outperforms the ablated versions, which shows that each component used in our method contributes to the overall performance. We also evaluate our method on the downstream task of gaze-based activity recognition. Specifically, we use the ground truth eye gaze, the eye gaze generated by our method, and the eye gaze generated by prior methods. We use such kind of eye gaze to do the gaze-based activity recognition. From this table, we can say that our method can achieve better recognition accuracies than other methods, and our methods is comparable with ground truth eye gaze. Well, we identify some limitations of our work. First, we ignore the influence of the visual scene content on eye-body coordination, because in this work, we mainly focus on the coordination between eye and full body movements, and thus we ignore the visual scene content. Second, our analyses are limited to indoor environments. This is because existing public datasets are all collected in indoor settings, and thus we would like to explore the outdoor settings in the future. Well, in the future, we would like to there are many avenues for future work. First, we would like to incorporate other modalities such as facial expressions and audio signals to improve the performance of gaze generation. In addition, we would like to explore the eye-body coordination for interactions between more humans or between a human and a human avatar. Because currently our human-human interaction analysis are limited to interactions between two humans. So explore more humans or humans between humans and human and a virtual avatar is an interesting avenue for future work. Finally, we would also like to generate stylistic eye gaze. For example, to generate eye gaze that can convey different emotions. Well, to conclude, the main contributions of our work are listed as follows. First, we conduct eye-body coordination analysis in diverse human object and human-human interaction activities. Second, we propose a novel method called Pose2Gaze that employs a convolutional neural network and a spatial temporal graph convolutional network to extract full body pose features for gaze generation. In addition, we conduct extensive experiments on 4 public datasets and demonstrated that our method can generate eye gaze with higher precision than prior methods. Finally, we conduct experiments on the applications of gaze-based activity recognition to show the effectiveness of our method. The code of our work is available at this link. Thank you for your listening. Here are the references used in the slides. I'm looking forward to your questions. Thank you.